Okay, so before we start today, does anybody have any questions for me? Nothing? All right. So now we're about to begin an extremely useful topic that you'll see again many times over the years. And really, these are the main reason for us to study probability is, at least in computer science, there's a few things that we've sort of seen. We've defined events and looked at the probabilities that they happen. But a really critical sort of random thing that we've not discussed yet is what's called a random variable. And you'll be a little bit surprised at the definition of this thing. So let's say for a probability space S, probability space, even just a sample space, a random variable or x on S is just a function. It's a function that takes an argument from S, so it takes an outcome as an argument, and it gives you a real number. Okay? So that's the definition of a random variable. So in fact, you don't even need a sample space. All you need is a set, and it's just a function that takes elements from that set and maps each element to a real number. Okay? So we've seen things like this before. In fact, we've seen the following example. When we roll two dice and take their sum. So in this sample space of rolling two dice, that's this set of ordered pairs, I and j, where I and j are integers, 1, 2, 3, 4, 5, or 6. So it's this 36 element set. Not important right now. It's a uniform probability measure over this set. And we've looked at, well, you roll two dice, then you add them up. So, you roll a 3 and a 4, and you say, well, I rolled 7. Or you roll a 2 and a 4, and you say, I rolled 6. So in that case, what's the random variable that we're talking about? Well, that's the random variable that should take any element of S. So an element of S looks like a pair, ij, and maps it onto the real number, I plus j. So there's an example of a random variable, one that we've seen before. All right? So familiar one. So here's another example. So let's say I toss 3 coins. So that means I have a sample space S, which consists of sequences of 3 coin tosses. A coin toss is a head or a tail, which we denote by H or T. And there's 8 elements in this sample space. And they look like that. So we get a sample space of size 8, and it's a uniform sample space, so the probability of omega is 1 over 8 for each omega in S. So let's define a random variable x, which will be, we'll write it, so just like events, we sometimes write random variables in plain language, and let's say x is the number of heads. Okay. All right, so that means if I want to write it out more formally, then I'll have something like, well, x of this one here, tails, 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 is equal to 0. There'll be another one, which is x of heads, heads, heads. That's equal to 3. In between that, we can have either one head or we can have 2 heads. Okay. So there's the random variable sort of written out in plain language, but really this is what it looks like, right? So if you want to know what the value is, just look here for one of these things. Just look here and you'll see it's either 0, 1, 2, or 3. All right. So far, so good. Let's define another random variable over the same set of outcomes. And let's say that's the random variable y. And maybe y determines whether or not you win some game, where winning the game is getting 3 heads or 3 tails. So you might say y is either a 1 or a 0. And that depends if omega is head, 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 or omega is tail, 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 and it's 0 otherwise. So just another example of a random variable. Does it satisfy the definition? Yes. It's a function from our set S onto real numbers. Yeah, 1 and 0 are real numbers. 0, 1, 2, and 3 are real numbers. So everything satisfies the definition. And that's all this is right now is a definition. Okay. So a few sort of basic things about this. These random variables, you can use them to define events. Sometimes they're really convenient in defining events. So for example, if I look at the event, well, in general, if I say, let's look at the event x equals x. then what is that event? Well, that just means you look in your set of outcomes and you keep exactly the ones where the function evaluated at that thing is equal to x. Okay. So, for example, the event x equals 0 in this example, well, when does x equal 0? X equals 0, there's only one element in S that causes that to happen, so that's just this set. On the other hand, the event x equals 2, well, that's all of these three things give you evaluate to 2 when you apply x to them. So that set is this one. Okay. Nothing new or terribly exciting here. We've already seen you can define events all kinds of ways just by saying something, and that means you have to figure out what subset of this sample space S this corresponds to. All right, so far so good. So, a few things we can do, and let's do them here just so we get a feel for this stuff. So since saying something like x equals 0 or x equals 2 defines an event, that means we can compute the probabilities of these events. So for example here's all the things that evaluate to 0, so we can say the probability that x equals 0, well, this is, there's only one thing that evaluates to 0, and it occurs with probability 1 over 8, so we get 1 over 8. On the other hand, the probability that x equals 1, well, that's a set of size, that x equals 1 is an event of size 3, so that's 3 over 8. And the probability that x equals 2 is also 3 over 8. And the probability that x equals 3 is 1 over 8. Okay. So let's keep that off to the side. And y is a little bit simpler. The probability that y equals 1, what's that? Yeah, 2 over 8, because there's exactly 2 things in this sample space where a y equals 1. That's when you get heads, 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 or tails, tails, tails. So that's 2 over 8. And the probability that y equals 0, someone said it, 6 over 8. Here that's easy because we didn't even have to list them because, y is equal to 1 or 0, so the probability that y equals 0 is the probability that y is not equal to 1, so we just use the complement rule, so it's 1 minus this, which is 6 over 8. It's all the other outcomes. All right, so we've got this notion of random variables now, and that's good. And random variables, they somehow give rise naturally to events. And here we see, for the same set, you can have sort of different random variables. Here's 2 examples of random variable, both for the same experiment. So we saw that events can be independent or not. So maybe the same thing is true for random variables. Because hopefully so, because we saw that independent events, somehow they're easier to work with, probabilities are easier to compute. So is the same thing true with random variables? Do we get to do the same stuff? And indeed, let me just carefully write down the definition. It won't be surprising at all, except that there's sort of another layer in there. So we let S, PR, be a probability space. And let X and Y be random variables on S. And we say X and Y are independent if here's what's different from events. You take any little x and little y, real numbers, then the probability that x equals little x and y equals little y should be equal to the probability that x equals little x times the probability that y equals little y. So what's the difference here? Well, when we talked about two events, that's all there was, right? When we talked about independence between events A and B, we would just say that the probability of A and the probability of B is equal to the probability of A times the probability of B. The difference here is that a random variable defines a whole bunch of different events, right? For everything that it could, every value that it could possibly take on defines an event. And so what you need is that all of those events, so every event that can be defined using X and every event that can be defined using Y, those things should be independent. So another way of saying this is exactly the definition of independence of events. So that's just saying the events X equals X and Y equals Y are independent. And that's for any choice of little x and little y. So let's test that definition because we have two random variables here, x and y. So this one, x, is the one that counts the number of heads in our 3 coin tosses, and y is the one that gives us a 1 if we get 3 heads or 3 tails, and 0 otherwise. So are x and y independent? Who wants to hazard a guess? No? You've all been burned too much before by these things? What's your intuition? Yeah? That they're not. And if we think about it, so the nice thing when they're not independent is we don't have a lot to check. We just need to provide a particular counterexample, right? So independent means for every value of little x and little y, this has to be true. So all we have to do is find a value of little x and little y where this is not true, and then we can immediately say big X and big Y are not independent. And well, this value, when y equals 1, that means we got 3 heads or we got 3 tails. So does that mean could we have gotten 1 head in that case? Right? It's either 3 heads or 3 tails. or if you like, 3 heads or 0 heads. So that means if y equals 1, then it looks like none of these two things can happen, right? Then x can't be equal to 2, and it can't be equal to 1. It can be equal to 0, or it can be equal to 3, but not these other things. So just to find our counterexample, let's take y equals 1 and x equals 1, and just make sure this works. So let's say the probability that x equals 1 and y equals 1, that is the probability of, well, x equals 1 is this set of 3 elements. And y equals 1 is the set with 1 element, 2 elements rather, this one and this one. Right? That's what it means. X equals 1 and y equals 1 means that the outcome was in this set. This is the event x equals 1. And it's in this set. This is the event x equals, or y equals 1. What's the intersection of these two sets? 0. It's the empty set. So that's just equal to the probability of the empty set. And the probability of the empty set is 0. Okay, so that's 1/2 of it. But then we should also check that that's not equal to the probability that x equals 1 times the probability that y equals 1. That's an easy one. The probability that x equals 1, we can read it off from over there. That's 3/8 times y equals 1 is 2/8, which is not equal to 0. And therefore, x and y are not independent random variables, because this does not equal to this. Okay? All right. Well, so let's define another random variable then. Let's say, take the random variable, so we'll make a note here, x and y are not independent. Let's define the random variable z to be, in plain language, we'll write it as it's a 1 or a 0, and it's 1 if the first coin toss is heads, and 0 otherwise, or 0 if the first coin toss is tails. So in particular, the event z equals 1 looks like this. And the event z equals 0, well, these are the things that start with tails. Okay. So what's the probability that z equals 1? There's a few ways you can think of it. Well, just look at the plain language definition. If the first coin toss is heads, z equals 1. I mean, that seems to happen with probability of half. But if you don't trust that, just look at this event, z equals 1. That's 4 things, each of which occurs with probability 1 over 8. So it's 4 over 8, which is also a half. And the probability that z equals 0, well, that's also 4 over 8 by looking up here, or by using the complement rule on the complement of z equals 1. Okay. Are z and y independent? So if I tell you that the first coin toss is heads or not, does that tell you anything about whether you got 3 heads or 3 tails? I don't see an obvious counterexample, which is annoying because that means we don't get to just pick a value of x and y and say, here's where they're not equal. Now we have to try all values of x and y, little x and little y. So we're going to have to do that. Luckily, there's only 4 things, right? 2 choices for y and 2 choices for z. But let's just check them. So if I look at the probability that z equals 1 and y equals 1. Okay, so that's the intersection of 2 sets. So z equals 1, here it is, and y equals 1 is this set. So what's the intersection between those 2 things? Yep. 3 heads is, there's only one element that's common, right? Z equals 1 means we're only interested in the sequences that start with a head, and y equals 1 means we're only interested in the sequence that's heads, 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 or the sequence that's tails, tails, tails. Well, tails, tails, tails doesn't start with a head. So that's just the probability of heads, heads, heads. And the probability of that is just 1 over 8, because it's one of the 8 possible outcomes in a uniform probability space. On the other hand, the probability that z equals 1 times the probability that y equals 1. The probability that z equals 1 is 1/2. The probability that y equals 1 is 2 out of 8, which is 1 out of 8. So unfortunately, we have to keep going because this one passed the test over there, and we have to equals 1, and y equals 0. Okay, z equals 1 means we start with a head, and y equals 0 means that we don't get heads, heads, heads. So what do those look like? Well, we start with a head, and we don't get heads, heads, heads. So that means for the next 2 coin tosses, normally there would be 4 choices for them, but one of them is excluded, the heads, heads, heads choice. So this gives us heads, tails, tails, heads, tails, heads, and heads, heads, tails. Right? And this is 3 elements. So this is 3 out of 8. And On the other side, if I look at the probability that z equals 1 times the probability that y equals 0, the probability that z equals 1 is a half. The probability that y equals 0 is 6 out of 8. So that's 6 divided by 2 is 3 out of 8. And indeed, again, these two things are equal. Probability z equals 1 and y equals 0 is equal to the probability z equals 1 times the probability that y equals 0. Okay. Would you like me to continue? I can tell you now that these things are independent. We need to check the cases z equals 0, y equals 1, and z equals 0, y equals 0. But we'll get the same result in either case. So would anyone like me to do that? Would anyone not like me to do that? Okay, good. Overwhelming majority in favor of not continuing with this boring exercise. So z and y are independent. That may or may not be a surprise to you, but it's not immediately obvious because y depends on all three of the coin tosses and z depends on the first one, so they have something in common that they depend on. So it wasn't obvious that they were independent, but somehow they are anyway. What do you guys think if we ask about z and x? Are they independent? So z says the first coin toss comes up heads. X is the one that counts the number of coin tosses. So are those two things independent? So if z equals 1, meaning the first coin toss comes up heads, can x equal 0? I have no heads. No. The first coin toss is heads, then the number of heads in my sequence is 1, 2, or 3. So in particular, we can show that they're not independent by looking at the probability that z equals 1 and x equals 0. That probability will actually be 0 because the intersection of those two events is empty. On the other hand, the product of the two probabilities should be 1 over 8 and 1/2. So not in particular, it's not equal to 0. So finally, z and x are not independent. Okay, good. So that's the boring stuff. Oh, almost. It's almost the end of the boring stuff. One last thing, and really it's just, it's what you would expect. Remember when we talked about independence of events, we had this easy version here where you only have two events and you ask if they're independent. And then we had the version where you have a whole pile of events and you ask if they're independent. And there was two definitions. So let me just write them down very quickly, but they're exactly what you would expect. So here's the definition. Let x1 to xn be a sequence of random variables . over a sample space S. Then what we'll say is x1 through xn are pairwise independent if for every little x1 up to little xn, the events x1 equals little x1, x2 equals little x2, all the way up to xn equals little xn are independent, are pairwise independent. Okay. So again, the only difference between this definition of pairwise independence for random variables and the definition for sequences of events is this extra layer that we have to do, where we have to basically define all the possible events we could define with x1, all the possible events we could define with x2, all the possible events we could define with x3, and so on, and check that those things are pairwise independent. And if I replace the word pairwise with the word mutual in both places, mutually, then it's the same definition as well. Okay. So mutually independent random variables, they're really the ones that are great to work with, because it doesn't matter what I tell you about any subset of them, it doesn't tell you anything about the stuff that's not in that subset. And that turns out to be really, really useful, and we'll use that a little bit later. But now I want to get to the real reason that we study random variables, that random variables are so interesting. So far they just look like more ways of defining events, but the real point of them is they allow us to assign numbers to our experiments. Okay? So I do some experiment, toss a coin, count the number of heads. There's a way to get a number. Or I roll 2 dice, and I add up the 2 numbers that I see there. It assigns a number to that outcome. So it allows us to assign a number to all of the things in our space. And the way we've been thinking about probability spaces is really in terms of experiments, right? We have a set S, we do an experiment, and we get some outcome in S with some probability. But now you can think of, we did that experiment, and what we got is a number. So the most natural thing to ask is, what's the average number that we get when we do this experiment? Okay. For example, I take all the people in this room, and I pick one at random, and they ask them to step on a scale, and they have their, some number comes up, it's their weight in kilograms, and that's fine, okay, so that's it, right? The experiment is, I take a person in this room uniformly at random, so the sample set is the people in this room. The random variable, x, is the thing that assigns each person their weight in kilograms, and then it really kind of makes sense for me to say, what's the average weight of someone in this room? So if I pick one at random, what's the weight that I expect to see on average? And that's where this next definition comes in. It's a really simple one compared to what we just did. So to set everything up, let SPR be a probability space. And let X be a random variable on S. Then the expected value of X is defined as, we use this notation, expected value of X. So what we do is we sum up, take everything in your probability space. So this is, each of the people in this room. I evaluate X for that thing, so I take that person's weight, and I multiply that by the probability that I picked that particular person. Or for each outcome, I look at the probability that I get that outcome and multiply that by the number that's associated with that outcome. And if we think about this experiment with people in the room here, I don't know what the number is. Let's say there's 50 people in the room right now. Then what is this doing? Well, this is saying you take all the people in the room, and let's say I'll pick them uniformly at random, so each one is picked with probability 1 over 50. So I take the person's weight and multiply it by 1 over 50. And then the second person's weight and multiply it by 1 over 50. And the third person's weight and multiply it by 1 over 50. So really, what does that mean? That means I'm just adding up everyone's weight and dividing by 50, which is what we think of as the average weight of someone in this room, right? You take all the observations of weights and you divide by the number of people in the room. That's the average weight. And I'll write out another way of writing this is to sum, and it's more convenient in many cases, over X, and you look at, okay? So this X ranges over, you can say over all reals, over all reals, but a better way to think of it is the following, because if you range over all reals, then you immediately get an infinite sum or an uncountable sum, so that's a bit annoying. Think of these two expressions here. This one is summing over all of the things in the set S, which in terms of this function x, these are all of the valid arguments for x. Okay. So this is the sum over, does anybody remember for a function, what is the set of its valid arguments? Remember what that's called? Yeah? Domain. It's called the domain. So this is the sum over the domain of x. And over here, this looks at all of the different values that x might take on and sums over those. So this is just the sum over the what of x? The range of x. And you get the same thing in either case, right? Because if you look at what's happening, call this the range of x. For everything in S, x takes it onto some real number. Sometimes two things go on to the same real number. So in one case, I enumerate the elements in S, look at this probability of this thing showing up, and multiply it by that number. In the other case, I look over here, I add up all the probabilities of these things showing up. That's what this is doing, and I multiply that by that real number. So in either case, basically, each arrow in this picture contributes the same amount. Okay. All right. Now, this is called the expected value. Sometimes it's also called the expectation. And sometimes it's also called the mean. And sometimes you might see it written as the average, but I would prefer if you didn't use that. Mean is okay, expected value I like, expectation is fine as well. But let's not call it the average, because average means something else in most contexts. All right, so let's do a couple of examples. This first one is a bit surprising. So if I toss a six-sided die, then I get the sample space S is 1, 2, 3, 4, 5, 6. And I can take the very natural random variable on S, which is to say that x of I is just equal to I. So if I roll a 1, then I get the number 1. If I roll a 2, then I get the number 2, and so on. So if I roll a six-sided die, what's the expected value of that? Which, this is where the word expected is a bit strange, because it sounds like, what's the value you expect to see? And I'll guarantee you that the value that you get for the expected value is not a value you expect to see in this case. Yeah. So turns out that the expected value when you roll a six-sided die is 3.5. Okay. So that's where mean is somehow a nicer word for it, because it removes expectations. So just apply the definition. So we need to sum over omega in S of x of omega times the probability of omega. That looks complicated, but what's S? S is the integers 1 through 6. And x of omega is just omega, so that's that thing, or x of I is just that thing. So I times the probability of I. When I roll a dice, this is a uniform probability space. So this thing here is just always going to be 1 over 6 for any particular value. So the sum I equals 1 through 6 of I times 1 over 6. So that it doesn't confuse us, this is a sum where every term is multiplied by 1 over 6. So let's just multiply the whole sum by 1 over 6 instead. And does anybody remember what Gauss told us about these things? 9-year-old Gauss said that sum like this, I equals 1 to n, is n times n plus 1 over 2. So we get 1 over 6 times 6 times 7 divided by 2. The 6's cancel, and we get 7 divided by 2, 3.5. So when we roll a 6-sided die, we get well, the average value or the expected value that we see is 3.5. And there's lots of ways to think about this. I mean, the right way, of course, is that it's just the definition, and we applied the definition, and this is the number we got, so that's what it is by definition. But sort of the reason the definition works this way is if we rolled this die many, many times, like we rolled it n times, and we added up all the values that we saw, actually what you'll find is that will get closer and closer to 3.5 times n as n gets bigger. Okay. So basically, it really does mean it's what you expect, or it's the average, but it's the average over somehow, if we did this many, many times, this is what we would, what would turn out as the average. Okay. All right. So that's sort of a baby space. Let's try another one. We roll 2 dice. All right, so this is us rolling 2 dice, call them I and J, the first one and the second one. We'll assume a uniform probability space like we always do for these dice rolling experiments. And let's take X is going to be a random variable, which means it needs to take pairs, I and J, and map them onto real numbers. And it'll do that by taking I and J and mapping them to I plus J. So I roll 2 dice and I add up the numbers that I see. It's the one we've seen already. So what's the expected value of X? Anybody want to hazard a guess? Yeah?
7.
Seems reasonable. Why 7? Okay. Is there anything on the board that would suggest 7? Yeah. Yeah. So somehow the suggestion is that the answer should be 7 because if I roll 1, it's 7 halves. So if I roll 2 and add them together, it should be 2 times 7 halves, which is 7. So we'll see that actually that's true, but we don't know that yet. Actually, all we have at this point is just this definition. And the definition has 2 sides to it. We can use either one, but neither of them is going to be pretty. So if we start working on this side, so that means we sum up over all omega in S, x of omega times the probability of omega. Well, that's going to be a sum that runs I from 1 through 6, and that runs J from 1 through 6 of I plus J times the probability that the first one is I and the second one is J, but this is a uniform probability space, so each of those probabilities, at least that part's easy, it's always 1 out of 36. So again, whenever we have constants inside the sum, it almost always makes sense to bring them in front like this. But now we need to deal with this thing. And to deal with this thing, well, we've got to fight with it a bit. So we got a 1 out of 36. If I just look at the inner sum here, then I see this variable j, which is something I need to deal with. But I also see this I, which doesn't change. Right? If I hide the outside part, all I see is this inner loop where j is running through this thing and I is not changing. So I gets added up 6 times here. Okay. So 1 over 36, the sum I equals 1 through 6 of 6i plus the sum j equals 1 through 6 of j. Okay. All right, j is running from 1 through 6. J, that one we know, right? If we add all of this up, this is Gauss again, right? Gauss tells us that this is 6 times 7 divided by 2. Six times 7 divided by 2. All right. That's good. Okay, so a couple of things we can do next. So I see a 6 here, and I see a 6 here, and I see a 36 underneath here. So this whole thing is multiplied by 6. This is divided by 36, which means we can get rid of all of these two 6's, and this is just 1 over 6. So I get I plus 7 over 2. And this one is easy. 7 over 2 is just a constant in here that appears how many times? Well, this sum has 6 terms, and so this appears 6 times. So this ends up being 6 times 7 over 2. And this one over here, this is the sum I. I equals 1 through 6 of this. That gives us 6 times 7 over 2. So we get 1 over 6 times 6 times 7 over 2 plus 6 times 7 over 2. The 6's cancel out. We get 7 over 2 plus 7 over 2. And indeed, we get the answer 7 that we expected. Okay, that was a lot of trouble. Seems like a lot of work. And indeed, it is, and it's easy to make a mistake. Let's try the other way of doing it. So instead of summing over the domain, we can sum over the range. So what's the range of values that we get here for when we roll 2 dice and take their sum? What are the possible outcomes? What's the smallest outcome? 2. We roll snake eyes, 2 ones, we get 2. And what's the largest possible outcome? We roll 2 6's and we get 12. So we could also try and do this by taking the expected value of x is the sum. applying this thing on the right. So some x of x times the probability that x equals x. So the values of x we need to consider, we just decided they are any integer from 2 all the way up to 12 of I times the probability that x equals I. Well, that's nice. Here we basically had a sum with 36 terms in it. Now we have one with 11 terms in it. There's one issue though. This probability that x equals I is not 1 over 11 anymore. Anybody remember what this one looks like? Yeah. So we start writing it out, we'll see that, okay, the probability that I roll a 2 is 1 out of 36. There's only one way to roll a 2, I have to get snake eyes. Probability that I roll a 3, that's 2 out of 36, because I can roll a 2 and a 1, or I can roll a 1 and a 2. And the probability that I roll a 4, that's 3 out of 36, because I can roll a 1 and a 3, a 2 and a 2, or a 3 and a 1. And this goes on times 4 out of 36. So the most likely one was 7, which gives you 6 out of 36. And then it starts to drop again. 8 is 5 out of 36. 9 is 4 out of 36. 10 is and then finally, the only way I can roll a 12 is if I roll 2 6s, so that's a 1 out of 36. And let me do this in my head. 7. Okay, so yeah, you can apply the second one. You get a smaller thing, but you have more difficult probabilities to work with. Neither of those seems great. Now let me show you the right way to do it. And this is, if you're talking about expected values, and actually, which is almost always what you're talking about when you're looking at things like when you're studying algorithms and the running time of algorithms, or the running time of code, things that are randomized, then yeah, it's expected values that is the first thing that you're interested in. There's this really, really important property called the linearity of expectation. And what's really nice about it is you take any two random variables, x and y, then the expected value of x plus y is equal to the expected value of x plus the expected value of y. Okay. So right now you should be, if you've really been following, you should be confused because what are we doing here? We added these two things, but what are these two things? These are functions. What does it even mean to add functions? We better say what this means, right? So x plus y denotes the random variable we'll give it a name, Z defined by Z of omega is equal to X of omega plus Y of omega for every omega in X. Okay? It's exactly the definition that you expect, but we need to define it somehow because X and Y are actually functions. If we remember what random variables are, what happens when you add two functions? Well, we use that to mean that we evaluate the two functions at the same points and add those two things together. Right? And that's allowed because X of omega is a real number and Y of omega is a real number, and adding them together gives us this real number. Okay? Okay, so this says if I want to know what the expected value of the sum of two random variables is, I only need to know the individual expected values of these things. This is extremely powerful for two reasons. One is this works for any two random variables. So we've seen very few things like this, right? When we looked at things like, how do you compute the probability of A and B? We always had, it's really easy if A and B are independent. This doesn't require that X and Y are independent. These X and Y can be completely dependent. They can be completely intertwined. In fact, X and Y can be the same random variable. There's no problem there. So it's powerful for that reason. And the other one is sort of the obvious philosophical one is it's letting us do divide and conquer. We have something complicated over here that we're trying to study, and we get to break it up into simple things. And we'll take that to the extreme later in the course where we'll have something really complicated that we want to study, and we'll break it up into a whole bunch of the simplest imaginable things, binary random variables, 0-1 random variables. But right now, let's see how it helps us with our dice problem. Or let's prove it first. So just proof. The proof is obvious. We have this Z here. So the expected value of Z, apply the definition, you sum over everything in the outcome set of Z of that thing. That's just the sum over everything in the outcome set of Z is defined as this, X of omega plus Y of omega. All right, nothing, this is just us expanding the definition of Z. Well, when we have a sum where each term has two parts, we can just split that into two sums. But wait a minute, this sum here, this is just the expected value of X, right? And this sum over here, this is just the expected value of Y. And so that's all linearity of expectation is telling us is, just apply the definition and you get the proof. I mean, once everything is well defined, it just falls out. All right, so someone over here gave us this annoying random variable, xij equals I plus j. It's complicated to study. How can we fix it? Well, we can fix it by defining two random variables. As follows. Let x1 of ij be I, the one that tells you the number that's on the first first die you roll. Let x2 of ij be j. Then what's x? Right? This is x of ij is just I plus j. That's all these things are. So writing using the more condensed notation, that just says that the random variable x is the sum of the random variables x1 plus x2. And linearity of expectation tells us that the expected value of x is equal to the expected value of x1 plus the expected value of x2. What's the expected value of x1? So what is x1? x1 is me rolling one die, right? That's the first die. So what's the expected value of that? It's right behind me on the board. 3.5 or 7 halves, however you want to say it. So this thing here is just rolling one die, 7 halves, 7. So finally, the pain-free way of figuring this out. And I think you see really how useful this is now, because what if I told you that I was rolling 10 die? I mean, if you had to do this, you would have 10 nested sums in there. You could work your way through them, and eventually you would get 35 would be the answer. Or you can use the obvious generalization of this, which I'll write down in a second, and you would get that it's 10 times 7 halves, which is 35. So here's the big generalization. Let x1 to xn be any sequence of random variables, and let a1 to an be any sequence of real numbers. So just think of all of these as 1 if you don't want to deal with them now. Then the expected value of a1 x1 plus a2 x2 plus a3 x3 all the way up to an xn is just equal to a1 times the expected value of x1 plus a2 times the expected value of x2, and so on, all the way up to an times the expected value of xn. We'll hardly ever use these a's here. Usually these a's will just be 1s, but know that you can put them there if you want. Right? And up here, this is the special case where a1 is equal to 1, a2 is equal to 1, and this is x1, this is x2. Okay. And this is the most useful thing that you will learn about probability in this course. It will allow you to tackle things that on the surface, when you first see the problem statement, you would think this is completely impossible. We'll never determine the expected value of this thing. And I mean things like, I give you some code and say, what's the expected number of times this line of code executes? You look at that and say, I have no idea. And we'll see that actually by using this and a few really easy tricks, we can nail those things down to like exact values for any particular distribution on inputs. Okay, that's a good place to stop for today.